Yeah, I feel extremely thankful to be gathered here on this land to share the joys of astronomy with you tonight. Tonight we have Felix Thiel, who is a PhD student here at Queen's. Felix did his undergraduate degree at McGill University. While there, he worked on the antennas for taking radio observations from the subantarctic, which you all use for albatross, a classic astronomy backronym. He's currently a PhD student working with Laura Fissel in our department, working on balloon bore VLBI experiment, or BFEX, a slightly more acceptable astronomy backronym. So without further ado, I'll pass you on to Phil, who will tell us about a beginner's guide to radio telescopes. Thank you.
All right, I hope everybody can hear me. Sounds like that works. Okay, well, thanks for the introduction, Lawrence. So this few words about this talk before I begin. So this talk will be a very different talk from, what we usually have at these open houses, in a sense that I will be mostly talking about methods today. I'll mostly be talking about how do telescopes work and all the kind of technology that is involved in actually producing these images that everybody uses for their science. My expertise personally is radio instrumentation, and most of what I will cover today is actually background. I will get a little bit in the end into what I do, but it's really important to kind of understand the background in this kind of discipline, which traditionally has been a discipline that has actually been driven by engineering rather than physics, right? The first radio astronomers were actually electrical engineers rather than physicists. So why do radio astronomy? Well, one answer is because we can. So light is an electromagnetic wave, and we can have these waves of all kinds of different wavelengths. Over here on this end of the graph, we've got X-rays. This small little band in here is what we can see, and then all the way over here is radio, right here, right? And it turns out that radio is actually one of the few wavelengths that our atmosphere actually lets through, apart from the visible light, right? So we have this huge window here where we can observe. So the brown here you'll see is actually, it shows you how opaque the atmosphere is at all these wavelengths, right? And apart from the visible, the radio is one of the few kind of windows where we can actually observe light coming from, the cosmos. So it's a big window. It spans almost 5 orders of magnitude in wavelength, going from about 10 meters all the way down to a millimeter. And what that means is that there's wide range of physics that you can study with it because of that, right? So what can we observe? And this is very much an incomplete list. I just put my favorites. We generally distinguish between continuum emission, which you can think of observing multiple colors of radio light at the same time. And we have spectral line emission, which you can think of as a single color. What can we see in continuum? Well, one thing you could look at is interstellar dust. This tells you something about how stars form the environments they form, right? You can look at radio galaxies. You can study how they, eat material. You can study the black holes at the center of these galaxies, which tells you something about general relativity, right? You can also look at time-varying objects like pulsars, for instance, which are like remnants of stellar explosions. And it's basically almost like a stellar dead body that's left over. And it has this very strong magnetic field. It emits lights and beams, and it starts rotating, and we can actually measure these pulses of light coming from these objects of pulsars. So for spectral line emission, we can look at molecular gas. So these are so it turns out that most molecules and atoms actually emit particular wavelengths of light that are very well constrained with physics. And by looking at those wavelengths of light, we can tell where this gas is present. So one of these things that we could look at is carbon monoxide, for instance. That's a tracer of star formation. We can also look at excited molecules. So we call masers, where the conditions are just right and you pump light from the kind of ambient radiation into your molecules, they start oscillating, they start vibrating. And then you get a similar effect to what you have in a laser pointer, actually. And you get this very bright emission of a single line of color. And you can use these to study star formation. You can use these to actually actually figure out distances to objects. If you know there's a water mazer nearby, you can use that. So a lot of things it can do. Finally, you can also look at atomic hydrogen. Hydrogen emits a wavelength of exactly 21 centimeters. And it will tell you something about galaxy dynamics, and will actually tell you more than what you can see from the visible. So here, these few galaxies here, they're actually, like, just from first glance, it'll be like, okay, yeah, great, there's a couple of galaxies. They don't seem to have anything to do with it. But if you look at where the hydrogen gas is, you get a more complete picture, right? So there's all these very different kind of effects of physics that we can study. Well, how do we observe? Well, first we need a radio telescope, like this, for instance. Has a couple of basic components. A dish, which is the primary reflector, secondary reflector, maybe a receiver, right? Or multiple receivers. And most importantly, you also need radio astronomers who can actually like interpret the signals coming out of this telescope and can make pretty images, right? So, but before I go into more details, we have to kind of review some concepts. So light is a wave, and it's a wave of electric fields and magnetic fields moving through space at the speed of light. There's a couple of little bit of jargon I'll be using here. The wavelength is basically the kind of length of one cycle of the wave. The amplitude is how big the wave is. And then we have this thing called the frequencies, is how many cycles does it go through in every second. And those are related together by the speed of light. So longer waves have lower frequencies and vice versa, right? The nice part about waves is that waves are very linear in the sense that they add. So if you superimpose two waves that where the peaks align, or we call them in phase, well, you get a wave that is twice as big because the peaks, they just add. And we call that constructive interference. And when we add waves that are out of phase, well, we get destructive interference. So they can actually cancel each other out, right? Okay, so this looks all pretty good. So how does this pertain to radio telescopes? So how do those telescopes work on the highest level? Well, you've got your photon coming in from outer space. It hits the dish, and then the dish is such that all the light, no matter where it hits in the dish, gets focused at a single point. And at that point, you place your radio receiver. The radio receiver does is it converts this electromagnetic signal into an electric signal. You can think of it kind of like AC currents coming out of a power outlet. So it's basically just a bunch of electricity that oscillates in time and oscillates at the same frequency as that radio wave. Well, then we need to turn it into something that a computer can read. So we convert those signals into numbers that a computer can read with this fancy thing called an analog to digital converter, or ADC for short, that basically turns this signal into data, right? Then we need to compute the output power. So we do this by squaring and averaging, but basically, why do we want the power? Because the power is a measure of how bright something is, right? Well, we dump it all on a hard drive. We have to save our data, right? And then at the same time as you record the power, you also record where the telescope can point. Now, those two sets of information can then be used to actually reconstruct an image, right? Because an image really tells you how much of a particular color you have in space, right? Any image that you'll download from the internet basically contains that information. And we're applying the same principles here, right? So then you put it into something called a data reduction code, which is a black box, even for some astronomers, because most astronomers didn't write it, and they kind of just use the software. So what that does is it basically combines these two pieces of information and then just kind of channels that into a file, which is an image, and everybody can use that for their sites. All right, so what happens exactly at the focus? Well, I told you that our light waves, they come in and they reflect off this dish and they interfere. So now suppose we have an object that is right head on. Notice how these waves, they travel exactly the same path from the top and the bottom. So that means they can interfere constructively focus, right? Now suppose all of these waves come in at an angle. You'll notice this wave travels a shorter distance than that wave. So what happens is at the focus, they destruct. So what does this look like? So we can plot this out. So on the y-axis, you have power, how bright the signal is. And on the bottom, you have the angle in arbitrary units. But so as we're moving head on, power goes up, and then as we're pointing away from it again, power goes down. Now you notice there's some width to it, and this has to precisely do geometry of telescope. And it turns out this width is given by the wavelength divided by the telescope diameter. So some of you might be thinking, okay, well, great. Okay, so this means that when we're pointing on our target, we get a signal, and if we're pointing off, we're not getting a signal. Well, this width actually has precise consequences. And what this means is that if you look at an object that looks like this, that is a point source, and by point source, I mean it's smaller than the block here, which we also call the main beam. Well, this is what it will look like. This is what the truth is, right? So really understanding these effects is really, really important when you do these observations. So we call these objects, they're smaller than the beam, we call them point sources. Anything that's bigger than the beam, we call that an extended object, right? So the resolution is therefore given by the size of the beam, right? So suppose we had two of these very close together, you wouldn't be able to tell them apart. So the important takeaway here is that we can increase the resolution by increasing the size of the telescope and decreasing the wavelength that we observe at. And what this also means is that if you just have one receiver, most radio telescopes actually are 1 pixel cameras. You can think of a radio telescope as a camera with just a single pixel that is only sensitive to one region on the sky, which is given by this, right? So what does this look like in practice? So here are two images. So this is a supernova remnant. It's a leftover of stellar explosion that happened not too long ago. It was actually reported by Chinese astronomers in the 11th century. What you see on the left here, this is an image taken by the ERM 30-meter telescope in Spain at a wavelength of about 2 millimeters. This one over here was taken by the large millimeter telescope at a wavelength of 1 millimeter. Now you'll notice that this is a smaller telescope, longer wavelength, bigger telescope, shorter wavelength. Notice there's a lot more small scale features in there than there is in this image. And that's because the resolution of these two is very different, right? This one has a lower resolution than that because the telescope is smaller and the observing wavelength is bigger, right? So the bottom line here is radio waves are big. So if we want a good resolution, we want a big telescope. Now the next part is telescopes are also like light buckets. So if we make a telescope bigger, that's a win-win situation for us because we'll collect more light and we'll be more sensitive, right? And point sources, so small objects, will appear to have the size of what we call the resolution or the beam, right? Okay, so here's some of the world's biggest. So this is the Green Bank telescope in West Virginia. This is the Epps-Beck 100-meter telescope in Germany. Those are the two biggest fully steerable telescopes on Earth. They're 100 meters in diameter. So just so you can get a sense of scale, that down there is a pickup truck, and that's a telescope, right? So those are really, really, really big, right? And another key difference, if you'll notice this one, for instance, looks a lot more like a TV satellite dish, and that is intentional because if you do that, you'll actually be sensitive to light coming out of like that direction. So what that means is your telescope won't be blocked by all your receivers. So this one will be much more sensitive, right? Okay, but there's never free lunch. Big telescopes are tricky. So we can have two effects here. So we can have either gravity. So basically gravity will try to warp your dish, and we have to adjust for that. The other thing is temperature gradients can be really, because objects expand as they heat up and they contract as they cool off. So if your temperature changes, the shape of your telescope changes. And that will kind of degrade the performance. So for instance, this is plot for my master's thesis. We're looking at a radio galaxy. That radio galaxy is not resolvable by the LMT, which means it's a point source. So we should just be seeing a blob of the size of the beam. And you can see this was sort of the case at the beginning, but as the night went on, this shape gets more and more oval, and then we're left with the smudge at the end. And that's because the telescope dish was cooling off, and as a result, we lost photons, right, over the course of the night. And big telescopes are also prone to structural failures. So one example of this 300-foot This was the predecessor to the Green Bank telescope. It took a lot of data. It was also part of a huge all-sky survey, the catalog, where they basically cataloged the radio sources, and that catalog is still used today. But on November 1988, it collapsed. And then conspiracy theorists went into a feeding frenzy over this. But the reality is not that the telescope was zapped by hostile space aliens, even though that would have been funny. What happened was a gusset plate on the structure, so that's the plate that holds together two beams that failed, and the whole telescope just came crashing down, right? Okay, so there's a limit to how big we can make these things. So how do we do better? Well, let's start with a big telescope. And let's split that telescope up into little segments, right? And let's take each segment and put it on the ground with its own receiver. And then we'll hook up to a magical machine called a correlator. So instead of just computing the square, so the power, you compute the power by actually multiplying signals of pairs of telescopes together. Well, we multiply and we don't add. You can ask me later. I don't have time to talk about that right now. But okay, so just to convince you why this works, let's just consider a single pair of telescopes. So that's something we often do in physics. We start with a small scale model and then we just make it more complicated. So let's just start with a single pair of telescopes. And to make it even simpler, let's just assume that both of them are pointing straight up at an object that is straight up. So you've got your light waves coming in. They're perfectly in phase because they travel the same distance. And we multiply them together. Now, the tricky part with multiplying them is we actually have to make a distinction now whether the number we get out is positive or negative, right? Because if this is positive and this is negative, well, it's negative. So if they're in phase, we get positive constructive interference. Now, if they're out of phase by a quarter wave or half a wavelength, then we get destructive interference because this one will read 0, and this will read the kind of maximum or minimum, right? And so on and so forth. And then as you phase out, now we multiply them together, but because we multiply them, we get constructive interference again, right? So what does the response look like? We can make the same plot as before, so angle and power, and you get this wavy pattern, which we also call interference fringes. And turns out that the width of these fringes is given by the wavelength divided by the separation between the telescopes, or what we in radio astronomy jargon actually call the baseline. So that means that this gets narrower the further we pull these apart, and it gets wider the closer we bring them together. And you can see this is sort of reminiscent of what we had before, right? But not quite. So then we can also consider, okay, what happens if we look at an angle? Well, now there's a phase delay between, right? So this wave will always hit this telescope sooner, no matter what we do. So we have to put in a delay. So we have to slow this guy down so that we can make the waves match here, right? And that means that our resolution here is actually degraded. So resolution is given by this distance, not this distance anymore, right? So this is very complicated, right? This means that depending on where I point, I get different resolution out, right? But something doesn't seem right. Remember, for a singles, we have this, and now we have this. Why is the response so bad? Even worse yet, you won't be able to tell where our points are. Right? It could be here, it could be there, it could be there, it could be there. We don't know. So, well, the answer is, remember how we kind of started with a big dish and we split it up and we just took 2 pieces out of it and we got that, right? So that means we have to add more, right? So by adding more telescopes, by adding more shorter spacings, you will see that our beam shape slowly improves. And this looks very reminiscent of what we had before, right? Okay. So that means an interferometer is like a single dish telescope with holes inside, right? So but there's another problem. We've only considered this in one dimension, right? So the top view doesn't look like that. So what that means is you get a really good resolution this way, but we have a really poor resolution that way, right? So it's directional. So it really matters in how we orient this thing, right? Okay, so then, well, what do? Well, you just add more telescopes in the other direction, right? And then like that, you get good resolution both ways. But there's still, you can still come up with directions where the resolution is bad. So ideally, you just want to keep adding telescopes, right? So what have we learned? Well, we can increase the resolution of interferometers by increasing the baselines, the separation between them. And we want as many telescopes as possible inside that array so it comes closest to a single dish telescope. No, but unfortunately, we can't like put telescopes, we can't literally the face of the Earth with them, even though some radio astronomers would really like to do that. So there's a trick. Well, we can use the fact that the stars will kind of, right, they will rise in the east and they set in the west. So what that means is that kind of the orientation of the sky above us will kind of slowly change. So this is the sky north and south, right? This is the projected baseline on the sky. So basically, if you would kind of shine a flashlight underneath this line, that's the shadow it would cast at each of the stages. And as you track your target, you'll see that the orientation with respect to the sky changes. So the longer we wait, the more kind of features we can sample. And that's what we call Earth rotation aperture synthesis. That's a fancy word for it. But that means by waiting longer, we can get more information, right? But even that is limited, right? Because you will only be able to, we can't look through the ground, for instance, right? So there's always some information missing. So that means there's never really a free lunch, right? So we want to add as many telescopes as possible, but the problem is there will always be, just because of the geometry of this, so if this is our array of telescopes, there will always be gaps in between, right? We can't put telescopes on top of each other. So what that means is we lose information. The information we lose is actually information about large things. So we get a lot of information about small things, but if we want to look at large things, we lose that information entirely. And these things we can observe given that short distance. So each baseline, so each pairing of telescopes will sample a different feature in your image. But so, and just to illustrate how this works, so this is an example of an interferometer. This is the very large array in New Mexico. It's 27 dishes inside the New Mexican desert. You'll notice it has this Y shape, and that's precisely to maximize the amount of features you can see with this telescope. And they can put this in different configurations. So you'll notice there's these railroad tracks here. And then when I change the configuration, they load all these telescopes in a red truck like that. And they kind of like just drive them up and down the tracks and put them in their new location. So the VLA comes in 4 different configurations, ranging from 35 kilometers down to 1 kilometer in diameter. You'll notice that, so this is an image of Hercules A, the gray galaxy I showed you right at the beginning. This is with the biggest configuration. You'll see all those beautiful small scale features. This is with the smallest configuration, all blurred out, but you'll also see a lot of large scale features that you didn't see in the small scale features and in the small scale kind of image, right? So that's kind of that's the drawback, right? I can make my interferometer bigger, but that also means I lose a lot of information down here, right? Okay, suppose we don't care about large scale features and we just really want to see how well we can do with resolution. So can we do better? Well, we already kind of increased kind of the lower part of this. Well, the other option is always to go to higher frequency. And then you have something like the Atacama Large Millimeter Array. The VLA was observing at wavelengths that were a centimeter long. This one observes at wavelengths that are about 1 millimeter long. So a factor of 10 bigger, it gave us beautiful images like this one. What you see here is the formation of a planetary system. You have a young star in the middle surrounded by this big debris. So that's how good the resolution is. Like this is the equivalent of resolving a penny at a distance of 120 kilometers, right? Can we do even better? Well, let's make the baseline longer. And then surprise, surprise, we call this very long baseline interferometry, or VLBI for short. And the main difference is we have a baseline of hundreds of thousands of kilometers. The first challenge here is that we have to kind of do that multiplication of data after the fact. We can't do it in real time because these telescopes are so far apart they can no longer talk to each other, right? So what you have to do is we really have to record the raw wave onto a hard drive. So we can no longer average it, right? So that means the amount of data you get is just enormous, right? Like even a small fraction of an observation with a telescope like this is enough to fill out, like 10 laptops, right? The second challenge is there is not a lot of telescopes, so you'll be missing a lot of information. And the third challenge is that each of these need the proper timing reference because you have to know when and where you're recording the signal, right? So there's a lot more challenges. This is very much a Canadian thing. So the first time VLBI was successfully done was in Canada using the Galt 26-meter telescope in Penticton, BC, and the Algonquin 43-meter, which is not too far from here, Algonquin Provincial Park. They had a baseline of about 3,074 kilometers. That was the first successful attempt at VLBI. But nowadays, I mean, we use more high-tech instruments than that. So the go-to instrument for this is the Very Large Baseline Array. It's 10 dishes all across the United States. They reach from Hawaii all the way to the Caribbean. They can even be paired with other telescopes that I showed you tonight in an even bigger array. And so that telescope gave us beautiful images like this one. What we see here is another radio galaxy. Its black hole is somewhere here, and there is this huge jet of material coming out because black holes, turns out, are very messy eaters, and they eject a lot of stuff when they heat it. And this is about 100 times the resolution of that ALMA image that I just showed you, right? So crazy resolutions. Can we do even better? Well, let's go to shorter wavelength. And this has been done. This was the Red Horizon telescope. And you might have seen this on the news somewhere, so they use these high frequency telescopes all across the Earth to produce the first ever image of the black hole shadow. And the reason why I say the shadow is with black holes, they don't emit light themselves, but what you can basically observe the light kind of emitted around them, and then you can see the shadow, right? And this resolution of this image is about 10 times higher than what the VLBA image had just a slide ago, right? So this is what it looks like. Now, can we do even better? Well, we can't really make the baseline any bigger because, well, we can't really make the Earth any bigger, right? We already have a telescope the size of the Earth. Can't go anywhere there. But we could try to go to even higher frequencies. Well, higher frequencies are tricky, and that's where we start off with the plot that I started at the beginning. Go to higher frequencies, we start hitting this wall over here. This is a cartoon, but what it really looks like is something like this. So if this number is really big, is infinite, everything is absorbed that comes into the atmosphere and lets everything through if it's at zero, basically. So the Event Horizon telescope was observing over here. And you can see as we push the higher frequency, this gets worse and worse. If you think this is bad, this is actually really good. This was made off of data from ALMA, which is like probably one of the best sites you can use for high frequency observing. Right. Okay, so what could we do with higher frequency? Well, we could observe more black holes. We could also get better resolutions on the existing observations. And so this is a plot: black hole diameter, black hole brightness. The key thing are these lines here. So those lines are the resolution of an interferometer the size of the Earth at a particular frequency. So this were the kind of EHT observations I just showed you. And you can see as we push to these higher frequencies, we can see more and more black holes, right? And this can tell us something about general relativity, for instance, right? So how we have two options here. Well, either we can go to space, where we don't have the atmosphere. We'll also have longer baselines. It'll be great, but it's really, really expensive. We all know how expensive James Webb was. The other option is we can try to do this from a balloon. We won't have longer baselines, but we'll have access to higher frequencies because we're above 99.5% of the atmosphere, right? And just to give you an idea of how much better we can do, This is kind of sort of the plot that I showed you before of the element side. This time in terms of transmission. So 1 means everything gets through, 0 means nothing gets through. This is at Alma. This is 40 kilometers above New Mexico. The reason we chose New Mexico was because in New Mexico, NASA actually has a stratospheric ballooning base there. And you'll see most of it gets through. You still see spikes, and that's basically from molecules in the upper atmosphere. But we're doing a lot better, right? So that's what we're working on here at Queens. We're actually building a prototype for this. So if you have a great idea and you don't have a lot of money, it's quite simple for the prototype. This prototype is called the Blue LBI experiment. It's called our BVEX for short. It will operate at 22 gigahertz. You notice this is 10 times lower in frequency than the BHD. And that's because we have to keep this simple. There's a lot of new technology we have to develop. And BVEX will not give us higher resolution, but what BVEX will do is it will help us develop technologies required to do high frequency LBI. So this is what the telescope looks like in our lab. You'll notice it doesn't have a gondola. That's because the Canadian Space Agency will be launching us, will give us the gondola, and it will actually be a shared payload with all kinds of other experiments on it. We'll be launching from Timmins in Ontario in the middle of nowhere, mainly because we want to make sure you do this in remote locations, that when the balloon comes down, it doesn't drop on anything, right? This is a very big effort. Really want to highlight the amount of undergrads that kind of working on this project. These ballooning projects are extremely useful for getting undergrads engaged. We have collaborators from all kinds of institutions. The whole thing is led by Laura Fissel here at Queens. And ironically, with this project, the easy part is building a telescope. Why? Well, because we've been building radio telescopes for the past 80 years. And with the kind of development of the SATCOM industry, it's become easier and easier to actually just get parts for radio telescopes on the internet, right? Because people build these routinely. So this was when this was before we actually had a proper mount for it. Let's have the kind of radio dish in the lab. It's about 36 inches in diameter. This is us in the machine shop actually putting together the kind of mounts for the telescope. We dragged it out to the football field, which is right behind this building one day to actually get it tested. We actually have one of our undergrads at the opposite end of the football field with a little transmitter, and then we're trying to kind of characterize the beam shape with that. This is the receiver. I won't go too much into how receivers work. If you want, you can ask me afterwards. But the main gist of it is, first you have to amplify your signal because it's very weak. And then you have to, because these signals are so high frequency, it's really hard to sample them. So you have to shift them to a different frequency. And that's what this box does. And then we feed it into our backend, our ADC, that these little tiny little boxes on that board up there. And then we save that on our disk, right? Okay, so technical challenges. So that was the easy part, was building the radio telescope. The hard part is actually doing interferometry. Why? Well, because interferometry hinges on you being able to adjust for this phase offset here, right? To adjust for the fact that both light waves will have hit the two different telescopes at different times. So we've got our balloon and our ground-based telescope, right? And the hard part here is more precisely when and where a signal was recorded. To motivate why the when is hard, well, balloons move around. So your balloon moves and you don't know about it, then your balloon could have moved by like hundreds of wavelengths before you even know it, right? So we have to track that position somehow, and our requirement for that is we need to know the position down to a millimeter, right? So that's like knowing the balloon like being here or like just a tiny bit over, right? And if we were to do this at 1.3 millimeters, it would be 0.1 of a millimeter, right? That's tiny, right? So the general idea is, fortunately enough, that there's a lot of good accelerometers in the markets that can track very small scale motion, and we'll be using those together with our GPS units. Now, the even harder part is the where, and just to motivate why this is a problem, I'll go off on a bit of a historical tangent, but this is kind of an analogy that always came up when I discussed this project with other people. So people in the 18th century had this very, very special problem, which was called the longitude problem. So this was way before the era of GPS. And we could not, it was really hard for them to determine longitude. And that was because you would actually have to measure the time when the sun was at its maximum height as a function of Greenwich Mean Time, so basically London time, right? This is all well and good if you're on land, but if you actually if you're actually on a boat, it becomes a bigger problem because in the time, they were using clocks that were actually driven by a pendulum. So if you have your boat rocking back and forth, and then your clock rocking back and forth, and the pendulum is supposed to keep your time, it'll also rock back and forth, and then your reading will no longer be accurate. Well, we're facing much of the same issues. We don't use pendulum clocks anymore, but nowadays we actually use these very high precision crystal oscillator clocks. The problem is that crystals are very sensitive to vibrations and very sensitive to temperature changes. Both of these things happen on balloons, right? The balloon moves around. It's like a giant floating pendulum, right? That moves back and forth. The bigger headache here is actually the temperature. So these are temperature readings of a balloon gondola on a Canadian Space Agency balloon flight. You can see exactly where the sun came up, mainly here. Why? Because all the temperatures, they start going up. And they get really, really hot because we don't have any air that can convect away all the heat, right? So once you get something hot, it stays hot. So you can get temperatures that go up to 100 degrees Celsius, right? That's like boiling water almost. So one of the main challenges is actually to keep this little crystal oscillator, tiny little silver box there, stable. And to do that, we have to keep our electronics inside this temperature control pressure container. And then to kind of adjust these drifts, we have this very complicated circuit that basically compares the signal from our clock to the signal from a GPS switch. Basically gets a signal from an atomic clock on the ground, right? So, yeah, so this is how I intend to do this. So to just wrap up, so VVEX will not give us the better resolution, but what we'll do will kind of help us understand what kind of systematics we're up against. And this will be very important once we want to do like high frequency radio observations with this. And with that, I'll take questions. Yeah, so we're hoping that we can get a flight of about 12 hours. This is obviously subject to winds in the stratosphere. So usually how these launches work is we get a 10-day launch window. Inside that window, every day they check the weather forecast.